All right, so last time we were talking about discrete time LTI filtering. We dealt with a very simple system. A filter whose impulse response had only two non-zero samples. And because its region of support, which is the interval over which its values are non-zero, was finite, we call that a finite impulse response or FIR filter. So in our picture, we had the impulse response. From the impulse response, you figured out that there is a difference equation that governs the input and the output. Linear constant coefficient difference equation. You also found from the impulse response the frequency response of the system. We may have used K or L in the previous lecture. It doesn't matter. The dummy variable of the summation is not so important. And we found that to be 1 plus e to the minus I omega over 2. And we massaged that term to figure out the frequency response plot. Yeah?
Yeah, well, last time we see that the magnitude response pretty much is the filter. But what's the phase response? Like, what is it?
The effect of the phase is more subtle. I'll go over one example in class where you apply a sine or a cosine to a filter like this, and you'll see what happens to that sine or cosine at the output. The phase essentially is, you can see the effect of the phase most conspicuously by applying a complex exponential of a particular frequency to an LTI system whose impulse response is small h, frequency response is capital H. And what do you know about the output? E to the I omega naught n. So the same frequency comes out. Scaled by what? H evaluated as omega naught. Okay? Now, H, in general, look at that summation. It's a linear combination of a bunch of complex exponentials where the coefficients in the linear combination are the impulse response values. So H, in general, is a complex valued function. In other words, you can say H goes from the reals to complex. For certain small h, capital H will be real valued, and we'll see examples of those. But in general, it's complex valued. Because this is complex valued, to see the effect of the phase, you're going to have to break this up into its magnitude and phase. So H, in polar form, H of omega is the magnitude times the phase. Okay? So what happens at the output then? At the output, you'll have H of omega naught. E to the I, omega naught plus the angle introduced, or the phase difference introduced by the filter. Okay? this is the amplification, how much the filter favors this particular frequency. For some omega naught, this value will be small. For some omega naught, this value will be large. For other values, it'll be in some intermediate range. And the phase of the filter tells you how much this sinusoid moves back and forth to the left or to the right. Now, the effect becomes very complicated when you have a signal that consists not only of this frequency, but other frequencies. You saw an example of an audio signal that I shifted the slide bar. And you saw how just changing the relative phase of one signal with respect to the one sinusoid with respect to the others mangled the overall sum of the signals. So the effect of the phase is not very easy to see. And in fact, it's so complicated that there are some filters whose magnitude response is constant. And all they do is introduce phase for certain bizarre applications. So at this stage, it's kind of premature to talk about what this phase actually does. You need a lot more equipment, like Fourier transform theory and so on. And we'll do a reasonable amount of that near the end of the semester. But right now, I want you to focus on the magnitude response. That's what your audio equalizer does. And that's the view we want to take for now about a filter. Yeah, question? There is. Thank you. Omega naught n plus. Yeah. So you can actually pull out this angle, and you'll have an n plus something or other. And it's a quasi-shift in the signal. Of course, you can't think of half-sample delays or fractional sample delays. But essentially, the effect of the phase is in that complex exponential. It's complicated enough for a simple exponential. It gets even more complicated when your input signal is a linear combination of these complex exponentials. But I want you to focus on this right here, because that's what's going to determine whether the filter kills a particular frequency or amplifies a particular frequency or just lets it go through unchanged. Okay, so we've got the impulse response in the time domain. We've got the difference equation in the time domain. We figured out the frequency response from the impulse response. But there's also a link from the difference equation to the frequency response. That's what I'm going to do next. So what is the link between the linear constant coefficient difference equation and the frequency response? So let's deal with our example right there. Y of n is equal to 1/2 x of n plus 1/2 x of n minus 1. There is a way to get the frequency response from the difference equation. And that's simply by letting x be a complex exponential of the form e to the I omega n. If x is this, what can you tell me about y? H of omega e to the I omega n. Okay? Because the system is LTI. Because system is LTI. Well, you look at the difference equation and you evaluate all the shifted versions. So if x of n is e to the I omega n, what's x of n minus 1? you see an n, you replace it with n minus 1. So it's e to the I omega n, e to the minus I omega. That's e to the I omega n minus 1. I don't have any other shifted versions of any signal in my equation in this particular case. So now I just plug in. On the left-hand side, I have what you told me, which is h of omega, e to the I omega n. On the right-hand side, I have 1/2 e to the I omega n, plus 1/2 e to the minus I omega, e to the I omega n. How do I get the frequency response? I'm trying to solve for h. Huh? Divide by e to the I omega n. Now, how do I make sure that that's not 0? Can it ever be 0? Why? It's always on the unit circle. We're guaranteed this isn't equal to 0 because it's on the unit circle. So when I do that, I get h of omega equals 1/2 plus 1/2 e to the minus I omega. That's exactly what I had before. So now we have the impulse response. We figured out the frequency response from there. In this particular case, we also figured out the linear constant coefficient difference equation. And now we found the link to the frequency response. You will learn later, as we go through this class, that these arrows also go the other way. Maybe I should put it with dotted line, just so that we know we haven't done it yet. And so these are different representations of the same system. I can represent the discrete time LTI system with its impulse response, equivalently with its frequency response, or with the linear constant coefficient difference equation. There's also a graphical method of representing this, which is the way you would implement this on a computer. So let's look at this system right there. I have an x of n graphical way. So this graphical way is called the delay adder gain block diagram representation. When I want to implement this, how many storage elements do I need to figure out the output at any given time? And how many storage elements do I need? How many delays do you have? Look at a difference equation. One delay. There's only an n minus 1 term. So when you want to compute the output, you take the input, you delay it. Let me draw that a bit earlier. You delay it. The output of a delay is x of n minus 1. And if I want to minimize the number of multiplications, I add these two, and then I scale it by 1/2, and that's what I get. So y of n is x of n plus x of n minus 1 times 1/2, the whole quantity. That's what I get. So it's x of n plus x of n minus 1 over 2, the whole thing. I need one storage element, one adder, one multiplier to implement this system on a computer. You should be able to go from here to the difference equation, and from the difference equation to the frequency response. So in other words, you should get used to reading these kinds of diagrams and also constructing these kinds of diagrams from the difference equation. So let's go back to the previous board. And put a fourth element in our graph, delay adder gain block diagram. From this, you should be able to go, actually from the difference equation, you should be able to go to the delay adder gain block diagram, and backwards. Maybe I should use a different line there so we don't get mixed up. Okay? If I give you a difference equation, you should be able to draw a block diagram. I may tell you implement the block diagram with the minimum number of delays, minimum number of adders, and minimum number of multipliers. And you should be able to do that. And I may give you a block diagram and tell you, write the difference equation. Give me the frequency response. And we'll also learn in some cases where you can go from the difference equation to the impulse response. And later on when we study Fourier transforms, you'll learn what this backward arrow is. Right now we have a way of going from the time domain to the frequency domain using this infinite sum. So this is the equation that allows you to hop from the time domain to the frequency domain. We don't yet have the equation that takes us from the frequency domain back to the time domain. That's the whole discussion with Fourier transforms, and that's much later in the class. So this is where we are. We can characterize LTI systems with their impulse responses. Not all LTI systems have a difference equation representation. I should make that note here. Note. Not all LTI systems have LCCDE representations, but a very important and large class of them do. Bonsai. Fine. Take a break. So the bonsai break was called just a tad bit early. You know, when I write a comment like this, it begs a question. What is that question? Exactly. So, an example of such a system. An example of a system that does not have, I should say, a discrete time LTI system that does not have an LCCDE representation. Unfortunately, the answer will disappoint you because we're not fully equipped to see why this is the case, but I will give it to you anyway. We've already seen the ideal low-pass filter, which is 1 over a certain frequency band. It passes all the frequencies between capital W, between minus capital W and W with amplification 1, and it kills everything else. And these are frequencies pi and minus pi. This is an ideal low-pass filter. Ideal low-pass filter. We call it ideal because there's no way you can implement this filter in the real world. The impulse response to this filter is sine capital W of n over pi n. And just for the record, W is between pi and 0. Here's the problem with this example, and that's why I said that it probably will frustrate you. You can't plug this into this equation to get the frequency response. And the reason is this function dies out in both directions on the order of 1 over n. So when you plug it into that summation, the frequency response formula, that summation doesn't converge. And the way we find the relationship between this function and the frequency domain representation is through some backflipping and gymnastics that you'll see when we study Fourier transforms. So right now we're only equipped to go from small h to capital H. We don't know the equation that takes us from capital H to small h. And that's why this link right now is tenuous. And so not yet ready for this. But you're fully equipped to understand this. The frequency domain representation of this filter is flat, so all frequencies between minus W and W pass without alteration, no phase change. It's a real value, no phase change. They go straight. And everything outside that band is killed. So if you have high frequency content beyond W, it gets killed. It doesn't appear in the output. And anything inside just goes unchanged. So let's, actually I don't want to erase that. So let's keep this here. So let's say my filter is pi over 3 to minus pi over 3. This is my filter. Okay? I give this filter the input 1 plus cosine pi over 4n plus sine 2 pi over 3n plus e to the I pi over 2n. By inspection, give me the output. What gets passed? What gets killed? 1 plus cosine pi over 4n. That's it. Because these, the frequency 2 pi over 3 and pi over 2, are outside the pass band. This is the pass band. And this is the stop band. And that's pi. Stop band. You don't have to break the cosine into complex exponentials. You don't have to break the sine into complex exponentials. Because this filter is real valued. Whatever it passes with amplification 1 and phase of 0. Its magnitude in the passband, it's 1, the number 1, real number 1. And the phase of the real number 1 is 0. And whatever it kills anyway. You don't care about the phase. 0 has undefined phase, but it kills it. So what comes out will be H. So let me actually label these terms. What comes out will be H of 0 times 1, which is e to the I 0n. That's what this 1 is, 0 frequency, e to the I 0n. This one, if you were to split it, would have been 1/2 e to the I pi over 4n times h of what? H of pi over 4, which is 1, plus 1/2 e to the minus I pi over 4n, h of minus pi over 4, which is 1. Plus, you do the same thing for this guy. Plus 1 over 2i, h of what? H of 2 pi over 3, e to the I 2 pi over 3, plus 1/2, so 1 over 2i, h of minus 2 pi over 3. See, this is the long way. This is the method that's going to distinguish those of you who are fluent with these concepts and those of you who are not fluent with these concepts on an exam. If you're fluent, you're going to write this right away, and you're going to say, this frequency gets killed. This is 0 frequency. The DC gain of the filter is h of 0, which is 1. So 1 comes out, unchanged. Pi over 4 minus pi over 4 is in this part. Each gets amplified by the same number. So if you start off with 1/2 this frequency plus 1/2 negative the frequency, because the amplification on both is the same, you can factor that out. In this case, it happens to be 1. So the same cosine comes out scaled by 1. And then you have the sine. Again, these two values are the same. They're both 0. E to the minus I 2 pi over 3 n. I forgot all the n's here. N. Plus this guy, h of pi over 2. Sorry about the clutter. E to the I pi over 2 n. So you either take my way or the scenic way. Depends on how fast you want to get there. So in terms of understanding what this filter does, you should have no problem. The problem is we don't know what this link is right now. Because on the one hand, we can't use this expression to go from here to here. So I can't even ask you to verify it. That summation doesn't converge. And we don't yet know the opposite direction. It turns out we established the relationship between these two using the equation that corresponds to this red dotted arrow. And that's where we deal with Fourier transforms. So you got to be patient. But I will tell you this. Any LTI system any discrete time LTI system whose impulse response can be decomposed into a linear combination of one-sided exponentials and by one-sided exponentials I mean alpha to the n, u of n, or shifted versions of these, or beta to the n, u of minus n, or shifted versions of these, has a difference equation representation. And this is a good lead-in to our next example. So if you can write an impulse response in terms of, say, alpha to the n, u of n, you can write this, you can show that this has an LCCD representation. Has, and that's going to be our next example. That sinc function here, this is a sinc-like function. This is a discrete time sinc, essentially. Cannot be written in terms of exponentials in one direction or the other, or a linear combination thereof. And that's why you run into trouble. So let's go to this example, and we'll see what I mean. So we're now moving into infinite impulse response. That's actually a misnomer, impulse response. It's understood that this is infinite duration, not infinite in terms of value. Infinite duration impulse response, or IIR filters. Let's do an example. And that's going to be our example, actually. H of n is alpha to the n, u of n. For now, I'll assume that alpha is real. For now, assume alpha is real and it's less than 1 in magnitude. Actually, let's keep it positive for now. Let's assume alpha is less than 1 and greater than 0. An example of this, when alpha is, for example, 1/2, is a decaying lollipop sequence. When we say one-sided, we mean that it's truncated on one side, either on the left side or on the right side. This one is truncated on the left side. So everything is 0 up until 0. Its value is 1. Then it becomes 1/2, 1/4, and so on. So this is h of n. I'm claiming here that if it has a truncated or one-sided complex exponential representation, or a linear combination of these terms, I can find the linear constant coefficient difference equation for it. What I want you to do with your neighbors is determine h of omega. Find the frequency response of this filter and tell me what you get. And I also want you to think about why I'm insisting that this alpha be between 0 and 1. How are we doing? Which groups are ready? That can't be right. I didn't ask you if you're confident about your answer. Do you need more time, or are you just banging your head against the wall? Okay, I'll give you one more minute. Please try to convert it into something that looks like a power series, and then you'll get the answer. And use the definition. What's the definition of h of omega? It's h of n e to the minus I omega n. Plug in the expression for h, figure out how it influences the limits of the sum, and then convert what's in the sum into a power series representation, and then the answer pops out. All right, I better see more hands up now. It's yours. Sorry, Meatball, I'm bypassing you today. And you are? Alex. Go for it, Alex. Louder, louder, Alex. Okay, because of the unit step, the limits of the sum change, and now they go from 0 to infinity, because for all negative values of n, the impulse response is 0 because of this unit step. Okay, Alex, go for it. So you have the power series from 0 to infinity. And Alex wants to pull the n out. And what are you left with? Alpha e to the negative I omega. And why can we use this formula? So this thing is lambda. Lambda is being raised to the nth power. And the absolute value of lambda is the absolute value of e to the minus I omega. And that's equal to what, Alex? And what can you tell me about this? It's 1. So this is equal to the absolute value of alpha. And you know that that's less than 1. And so you can use the closed form expression for the sum. And what do you get, Alex? Negative I omega. Very good. So h of n being the one-sided exponential where, now I'm going to put the most general form. If the absolute value of alpha is less than 1, you can apply this method. I wanted to make it simpler for you by saying it's real value, then it's positive. So here it's sitting, alpha is somewhere here, and I've drawn it for alpha equals 1/2. But in reality, alpha can be anywhere strictly inside the unit circle. As long as it's strictly inside the unit circle, you can go through the same process. And being strictly inside the unit circle can be represented with this inequality. In that case, h of omega is 1 over 1 minus alpha e to the minus I omega. So that's our frequency response. I'll talk about how to plot the magnitude response of this filter a little later. Hopefully today, but if not, then certainly on Thursday. But I want to also make the right now I want to make the connection between this kind of a filter with a one-sided exponential representation and a difference equation representation. So let's do some reverse engineering. Look at the difference equation y of n is equal to alpha y of n minus 1 plus x of n. There is a fundamental difference between this difference equation and the one we used, or we saw, for the finite impulse response filter. What's that difference? It's recursive. This is a recursive difference equation. In the other case, you had no recursion. For finite impulse response filters, there is no recursion. Recursion is characteristic of IIR filters. Well, IIR filters that have IIR filters, I'm talking now about filters that have a difference equation representation to begin with, of IIR filters that have difference equation representations. And we're going to limit our discussion to linear constant coefficient difference equations. I'm not going to go into nonlinear difference equations. Now, I showed you a method by which you can look at a difference equation and figure out the frequency response of the filter that that difference equation represents. So I want you to do this, do what we did in the previous case, apply it to this, and verify for me that the frequency response of this filter is exactly that. Determine h of omega, or we'll call it h of omega even for this case, even though right now we don't know that it's going to be the same. It ends up being the same. H of omega for the system with the LC, let's simplify the. Determine h of omega from so do that and tell me what you get. Alpha has the same restriction. Why do I insist on alpha having the same restriction? Let's say I'm solving it exactly in this way. I'm solving it going forward in time. So y of n is alpha times the previous value of y plus x of n. This says the output at the current time is alpha times the previous output plus the current input. The output at the current time is alpha times the previous output plus the current input. If alpha is, and by the way, whenever you have difference equations, you need to have initial conditions because you can solve these difference equations in different ways. I'm going to assume that I have 0 initial conditions. Assume y of n is 0 for all n less than 0. 0 initial conditions. The system is at rest at time, up to time n equals 0. And now I'm going to solve the system from n equals 0 going forward. I apply an input, and I look at what the output is. Okay? Go ahead. After you do that, if you have extra time, draw the delay adder gain. Draw a delay adder gain block diagram. Implementation. For the system. Go for it. Remember what we did in the finite impulse response case. What did we assume the input was? Complex exponential, e to the I omega n. So do the same thing here. Alex, you get to pick. The Green Party. Start.
So we're going to use that definition to find h of omega. But before we do that, we have to find
What definition?
the infinite series.
How are you going to apply it here?
Well, first we have to find h of n.
Ooh. Well, you can go about it that way, but that's going to take longer. Going from the difference equation to the impulse response is not always easy. It's doable in this case, and we'll certainly do that. But I want you to do it the quick way, from the difference equation going to the frequency response. Remember I asked earlier, what are you going to do with the input signal? And people said, assume x is this complex exponential. If x is that, what's y? H of? H of omega. E to the I omega n. So now plug these two into the difference equation. On the left-hand side, what do you have? H of omega e to the I omega n. On the right-hand side, what do you have? E to the I omega n minus 1. I'm going to put the minus 1 up here. Plus e to the I omega n. And now what do we do? You got e to the I omega n's here. I don't want any n's in the equation anymore. I want an expression in terms of omega only, and I'm trying to solve for h of omega. That's what I'm trying to find. So what do you do with the e to the I omega n's? Divide them out. So this one divides out to 1, 1, 1. And what do you have now in terms of h of omega? Group all the h omega terms together. And so h omega is and this is exactly what we had up here. Okay, so the frequency responses are the same. Now let's do what you wanted to do at the start, which is find the impulse response. How do you find the impulse response? What do you set the input equal to? The impulse. So to find h of n, let x be the impulse, that innocent-looking signal. Okay? When the input is the impulse, the output we call the impulse response. And so instead of calling it y, I call it h. So the same recursion holds, except now wherever I see a y, I replace it with an h. Alpha h n minus 1 plus delta of n. Okay? And h of n is 0 for n less than 0, because I've told you the system is, the output, whatever it is, it's 0 for negative time. Now let's start going from n equals 0. H of 0 is alpha times h of minus 1, which is 0, plus 1. So h of 0 is 1. H of 1 is alpha times h of 0 plus. So from this point on, the delta n doesn't contribute anymore. Delta n was non-zero only for n equals 0. And from this point on, it doesn't appear. All these second terms are going to be 0. I'm going to write it explicitly here. But, so this is equal to what? Alpha. H of 2 is equal to? Alpha squared. H of n, alpha to the n. So you can now summarize and say h of n is 0 for n less than 0, and it's alpha to the n for n greater than or equal to 0, which is the same as saying h of n is alpha to the n u of n. And now we've closed the loop with the previous example. It's not always easy to figure out the impulse response from the difference equation. But in this particular case, you see the pattern after you write out a few terms. So now we have the impulse response, the LCCDE, the frequency response, and we went from here to here. We went from here to here. In the previous part, we went from here to here. And now you're beginning to see all these links filling up between all these nodes of the graph. What we haven't done yet, and it looks like we're going to have to postpone that till Thursday, we haven't drawn the delay outer gain block diagram. So do that, and we'll see you on Thursday. Oh, I'm going to have, before I forget, tomorrow, let me just check my calendar, make sure I'm all good for tomorrow. Tomorrow, Wednesday, from 2 to 4, I'll have walk-in hours. So those of you who wanted to talk to me about your performance, come see me in 493 Quarry.